So, we have in the last lecture seen how to represent operations of a bunch of transactions that are occurring together, and we call that as a schedule, and then looked at what is a notion, what is this notion of serializable schedules. So, serializable schedules will actually give us a good way of running the transactions, because the serializable schedules, one can show that they can actually avoid all these problems that arise due to the transactions trying to access the same database item and then trying to update them. Now, we have also seen how to detect whether a particular schedule is a serializable schedule or not, complex serializable schedule or not. Okay. So, to actually complete that discussion, I need to also introduce one more notion of serializability called view serializability. So, there is a so we will actually not go into much more detail about this, but this is the general notion of serializable schedules. That means these are somehow equivalent to serial schedules. Serial schedules is this class of schedules that are there inside this. Conflict serializable schedules are a larger bunch of schedules, larger set of schedules. You can see why this is a larger bunch of schedules, because serial schedules don't allow you to do any interleaving of operations at all. Whereas here in conflict serializable schedules, we do allow interleaving of operations of schedules, and so you get a larger bunch of bigger set of permutations of operations. Now, there is also one more notion called view serializability, and that's actually offers you a larger chunk of schedules compared to in conflict serializable schedules. So, let me define that in the next slide. So, a schedule S1 is in a similar way to conflict equivalence. We will now define view equivalence. So, schedule S1 is view equivalent to S2 if these conditions are satisfied. So, if any transaction Ti read the initial value of the DB item X in S1, then it also does so in the other schedule S2. So, in both S1 and S2, if Ti is the one that read the initial value of some database item, okay, if some transaction has read, it will be the same. Actually, it will be the same in both S1 and S2. So, for every DB item, what the transaction that reads it first is same in both. And if a transaction Ti reads a DB item X written by some other transaction Tj, then the same thing happens in S2 also in the same relative order. Then for each of these database items, the transaction that wrote the final value for the X is again going to be the same in both S1, S2. So, if this is the case, we call a schedule S1 as view equivalent to schedule S2, and so using this notion of view equivalence, we will define view serializable schedules. A schedule is said to be view serializable if it is view equivalent to some serial schedule. This is very important. We are not bothered about any particular serial schedule here. It's equivalent to some serial schedule. Okay. So, we will not go more deeper into view serializability. Let us see, we have understood conflict serializability, and let us see how we can actually realize conflict serializability in practice. Okay. Notice one thing here, that we have taken a peek at the the sequence in which the operations of multiple transactions are actually occurring, okay, and then said that some of these histories are permissible, some of these histories are not permissible. Especially we are looking for those histories that constitute conflict serializable schedules, and we have a way of checking whether that is conflict serializable or not. Okay, given this history, we will be able to check. All this is fine, but then transactions are actually running simultaneously. I mean, they have been submitted, and then the system is actually running them. Okay, so is it practical to kind of stop the system, take a history, and then say that, oh, whatever you have done in the last 1 minute is okay, but what you have done, how do we actually realize this? If what you have done, you have taken a history, look at the history, and then say, okay, this is not good, then what do you do? Practically realize this. So there comes a very beautiful idea. So we will talk about this in this lecture. So before we go into that, let's introduce locks. You are actually already exposed to locks in operating systems context, because locks is the established mechanism through which you will be able to get mutual exclusion, right? So we will make use of locks. So we will see how we can achieve concurrency control using locks. So the assumptions that we make here is a transaction requests for a lock on a DB item X before it is either doing reading or writing of the. So we will go for a simpler model where we use binary locks. Okay. So it is asking it has to ask for a lock, obtain that, and then either read or write on the database item, and transaction unlocks it after it is done with this. And so we will also assume that there is a locking scheduler or locking manager, which is kind of keeping track of the situation. So the binary locks, we will assume they, as you have studied in operating systems course, they will ensure mutual exclusion. So at any point of time, at most one transaction holds a lock on some DB item, right? And who is holding the lock is going to be kept track of by this locking scheduler. So we will assume that there is a locking scheduler. Now, just having locks by itself actually doesn't ensure serializability. So I have taken that same example which we have been looking at in the last lecture, which is actually not serializable, and introduce these locks, lock X, unlock, read item, unlock it. That's what I will replace this Rx by lock X, Rx, unlock X. So it's actually to be expanded as a sequence, and like that. So before every operation, I've simply introduced locks, but then the fundamental nature of the schedule actually has not changed. So it will continue to give problems for us. The conflict, it doesn't guarantee conflict serializability. So here comes a very important idea as to how to make use of locks and actually be able to realize conflict serializable schedules. We introduce what is called two-phase locking. Have you heard about two-phase locking in any other context? Okay. So two-phase locking is a locking protocol that has to be followed by all the parties, and all the transactions have to now simply follow this particular rule. What it says is that all lock requests of a transaction have to precede the first unlock request. Okay. So let me state it again. All the lock requests, so you keep on making, for every accessing any DBAS item, you have to lock it first and then unlock it. Now what this is saying, this 2PL protocol is saying is that, so keep on asking for whatever locks that you want, okay, and after you issue the first unlock operation, don't ask for any more locks, okay. So it is going to have two phases. In the first phase, you keep on asking for whatever locks that you want, because if you want to access database items, you need locks. So you keep asking for locks, and then operate on the items also, simultaneously operate on those items, because you have acquired a lock, you can operate on the item. So keep on doing that, but don't release locks if you still have an intention of asking for one more item. If you have an intention of asking for one more item, don't release the lock. The first time you release a lock, unlock it, then after that you cannot again ask for locks. You keep on unlocking only. So that's what this protocol says. A transaction has a locking phase followed by an unlocking phase. So this is a real simple, beautiful rule or protocol, and what we are going to show is that if all transactions follow this simple 2PL protocol, nice, beautiful protocol, then one can actually argue that the resulting schedules will be conflict serializable. Resulting schedules, whatever be the, so this is a beautiful way of realizing conflict serializability. Otherwise, what option you have? You have to stop and then look for the history and then check whether the history that has happened is conflict serializable or not. They are not practical. But what is practical is that you say, okay, here is a rule, all of you follow this rule, and if all transactions follow this 2PL protocol, then the resulting schedules will always be conflict serializable. Okay. So a major problem of how do we ensure conflict serializability is solved by this simple protocol called this two-phase locking protocol. So very, very important and valuable result for us in practice. Now, in the remaining part of the lecture, let me argue as to why exactly, how exactly this 2PL protocol allows conflict, only conflict serializable schedules. Why 2PL actually works. So this kind of involves trying to make a proof, right? So we make a small proof here. Not very difficult actually. It's not compared to the other proofs that we have seen. This is a very simple proof. So let's look at it. Okay, let's look at it. So S is a schedule of some n transactions, all of which are following 2PL. Okay, all of which we assume that are following two-phase locking protocol. Now, let Ti, one particular transaction, Ti be the transaction that issues the first unlock request among all the transactions. There are a bunch of transactions, or some n number of transactions. So if you now look at the schedule, so in the schedule now, in addition to the read-write operations, we have also the lock and unlock operations. So let us denote them by L subscript I and U subscript I, and they are locking specific items. So Li of x, Ui of x will come into the picture in the operations. Okay. So if you look at the schedule, it's easy to find out as to what is this particular transaction that is issuing the first unlock among all transactions. Very easy to find. Let that be Ti. Okay. Let that be Ti. The Ti is the one that issues the first unlock request among all transactions. Okay. now what we will argue is that all the operations of this particular transaction Ti, can be brought to the beginning of the schedule, without passing over any conflicting operations. Okay. So, if you imagine this transaction, I mean the history or the schedule as a long chain of these operations. So, the Ti is the transaction that issued its first unlock operation compared to all the other transactions. Now, the Ti's operations are spread somewhere here, right? Somewhere in the schedule. So, my argument here is that we will going to argue that I can take each of these Ti operations and then actually swap them all the way to the beginning of the schedule. When can you swap? As long as it does not conflict with the preceding operation, I can swap it, right. So, my argument here is that the operations of Ti can be brought to the beginning of S without passing over any conflicting operation. Suppose we are able to show this, then from S we will get a new schedule called S1. From S we will get a new schedule called S1, where all the operations of Ti are all together, followed by operations of all these n minus 1 number of other transactions. And S1 is actually conflict equivalent to S, because as I told you that we are able to bring the operations of Ti to the beginning of the schedule without passing over conflicting operations. So, because of that, this S1 will be actually conflict equivalent to S. Okay, so if we succeed doing this, now we have reduced S to S1, where operations of Ti come first, and then the operations of n minus 1 come. Now we can actually do an inductive argument and then say that, okay, now let me focus on these n minus 1 transactions. Among them, let me find out what is the one that has the first unlock operation. I can repeat the same argument and then bring the operations of that particular transaction all the way to the beginning of that S1, I mean this part, and then continue doing that. Then I will realize, I will be able to show that this S, the initial S that has been given, is actually conflict equivalent to some serial schedule, in which you can also see what is that serial schedule. In that, the operations of the transaction that issued the first unlock operation will come first, then the operations of the one that gave next unlock operation will come next, like that, in the order of the unlocking of the items. So, this is beautiful, right? So, so let us see how actually we can do that. So, all that now remains to be seen is that how can I actually do this, that the operations of Ti can be brought to the beginning of S without passing over any conflicting operations. If we are able to show that, then we can repeat that on the remaining part of the schedule, and then be able to convert this given schedule to a serial schedule, and so the given schedule is actually a complete serializable schedule, right? Okay, so now let us focus on that part again. Let us focus a little bit on that part. So, this argument will happen by proof by contradiction. Okay, so let us see. Suppose some operation of Ti, say Wix, is conflicting with some preceding operation, say Wj of x in the schedule S. Let us assume that. So, if you assume this, suppose we are led to a contradiction, then we can show that such kind of a thing does not exist, such a kind of thing does not arise. Okay. So, let us assume that, let us suppose that operation Ti, some operation of Ti, let us take it as Wif of Ix, is conflicting with some preceding operation, and let us also choose that Wj of x in this schedule is. So, that means it is happening like this, Wjx comes. So, the schedule is having some preceding operations, Wjx comes here, and then after some time Wix comes. So it's kind of now if such thing is what is actually happening in the schedule, then we can now insert the lock and unlock operations, right. So, Wjx must have done an unlock on x, only then I can, this transaction Ti can do a write on that, it can lock it and then do a write on that. So, so Uj of x is represents the unlock of the transaction j on the item x, must have happened. After that, lock I of x must have happened, only then Wix must happen. So, this is how this sequence can be. Now, let us bring in the assumption about Ti. What is the assumption about Ti? Ti is the transaction that did the first unlock among all the other transactions. So, it did some unlock, okay. So, obviously that unlock must have come here, because this unlock is happening here. So, as Ti is the first transaction to issue an unlock, let us say Ui of y on some item, it has released a lock. So, this Ui must precede this, because this is also an unlock operation. So, but we know that Ti is the one that gave the first unlock operation. So, Ti unlock operation Ui of y should come somewhere here, okay. But that immediately you can see is a contradiction, because the transaction Ti is forced to put his unlock here, and then after that lock this item x here, okay. Then transaction Ti is not actually following the 2PL protocol, because after it has done an unlock, it cannot ask for a lock. So, Wjx, Uiy, Ujx, Lix, Wix, this kind of sequence cannot occur if Ti is actually following 2PL protocol. So, this leads to a contradiction about the assumption that we made that all the transactions follow 2PL protocol. So, is that clear? No. So, Ti is not following 2PL protocol, which is a contradiction. So, what actually it means now is that our assumption that there is some Wjx that precedes Wix exists, okay. If we make this assumption that Wjx precedes Wix, all this sequence of arguments coming into picture and leading us to a contradiction. So, we can now conclude that such a pair does not exist at all. Such a pair of operations does not exist at all. We cannot find such a pair of operations. If we are able to find such an operation, then we will actually come to a contradiction saying that the transaction Ti is not following 2PL protocol, but we made an assumption that everybody has to follow 2PL protocol. Okay. Now, actually for this particular pair Wi and Wj is not the nothing very particularly important about them. you can actually take any pair of conflicting operations Wi, and this could be Ri of x, and then that could be Wj of x, or as long as one of them is a right operation and both of them are dealing with the same database item. So you can take any pair of conflicting. So argument is same for any conflicting pairs of operations involving an operation of Ti. So if you make such an assumption that some operation of Ti conflicting, so some operation that conflicts with the operation of Ti exists before that, precedes that, we are led to a contradiction. So we conclude that there is no such operation, and if there is no such operation, then for all these operations of Ti, there are no conflicting operations that precede it. Okay. If there are no operations that are preceded, then what I can do is to take these operations of Ti and then actually swap them all the way to the beginning of the transaction, the beginning of the schedule. So beginning with the first operation of Ti, we can swap operations of Ti with the previous operations and bring them all the way to the front of the schedule. Okay. So because of that, we can show that 2PL indeed always guarantees that we will end up with conflict serializable schedules. So yes, the schedule that we started off with is conflict equivalent to this particular serial schedule, where operations of Ti come first, and then the operations of the other transactions in which the second one will be the one that has issued the next unlock first, and things like that. Now, so this is good, right? This is the best thing that can happen. So 2PL is the one that saves us, because it is the one that if you follow this protocol, if all the individual transactions follow this protocol, then the whatever sequence of operations that actually ensures that actually happens turns out to be conflict serializable. So, and of course, I didn't explicitly show here, but we can see that from the definition itself that these conflict serializable schedules are really desirable schedules, because they will avoid all those problems of lost updates and repeatable reads and dirty reads and all that. Okay, you can show that later. We can also walk through that. Okay, now as you know, if you use locks, there is also a possibility of deadlocks. So deadlocks may occur. So what normally is done in database systems is to do a deadlock detection and resolution. So you can actually construct this wait for graph as to the transaction processing subsystem will now admit transactions and then keep on checking whether who is waiting for whom. So you can construct a wait for graph, and as long as a cycle comes into the picture, as long as a cycle does not come into the picture, you are safe. So you can keep on allowing the transactions to operate. If there is a cycle, then you know that deadlock is happened, and so you can actually break that cycle, take a particular arbitrary transaction from there, and then simply abort it. So the transaction processing system is going to have a control on who is going to succeed, who is not going to succeed. So it is going to just pick up one transaction arbitrarily and then say resubmit that transaction again. It will break the deadlock and then Good. So, with the combination of using two-phase locking protocol and deadlock detection and resolution, we will be able to actually realize a concurrency control subsystem, which will ensure that the transactions are happening in a safe way. You know, they are so with that, actually, I will stop for today, and then I will take up the issues connecting with system failures, crashes, and how they influence the schedules. So, the schedules are happening, but we also have to take into consideration the issues from system failure point of view. So, what are the various considerations that come from system failure point of view and how they affect this transaction interleaving? We will discuss in the next few lectures, where we will actually take up more detailed recovery procedures and things like that, and then discuss how